What I'll do is now go over the second worksheet, which is on radiometer characteristics. So just a short recap, what we did in the morning session was calculate the current in an antenna feed, and we found out how one can extract power. Now what we'll do is we'll relate the intensity of radiation that is falling on an antenna and see what kind of electrical power is received by the radiometer. So the antenna feed is what takes in the noise or the noise from the radiation outside and passes it on to the radiometer, with which we can measure it. So going by this definition from this book on essential radio astronomy, which by the way is a good reference. You can it's the most of the content is available online for anybody to access. Um, you could find a lot of things that were covered today described over there as well. A radiometer is essentially a receiver that is used to measure average power of the noise from a radio telescope in a well-defined frequency range. Now, let's try to visualize what's happening. Let's say there is a sky distribution of intensity. So that is what is represented over here. This is a picture that I found in the NRAO website, where what they have done is put a background of, instead of the visible light intensity distribution of the sky, they've taken a radio image, a large field of view radio image, and then made it look like that is what we are seeing in the sky. So you can imagine such a distribution that an antenna would see, and you can describe it in terms of the intensity as a function of the two position angles in the sky. Now, what one can do is introduce an antenna, a simple dipole would do for our purposes. And what we want to know is how does this antenna actually view the sky, and what is the power received by the antenna as due to the intensity that is falling on it, due to the combined intensity. So what one needs to understand is the intensity will couple to the antenna's electrical power through something called the effective area of the telescope. Now, I'll do give a small illustrative example of how to understand what this effective area is. So what we'll do is we'll take a dipole antenna. First, we will see it as an emitter, a transmitting antenna, and we'll see what the power pattern looks like, and then try to understand how it would be for a receiving antenna. So the steps are essentially, we'll try to see what are the motion of charges in the feed element of a dipole and how that leads to a distribution of electric field around it and hence the power. Then we'll see how we can translate that to the motion of charges in a receiving antenna, and we'll see the distribution of the effective area. So again, to the right, you'll see a small schematic of a dipole antenna, but now the difference is it's a transmitting antenna where an oscillating voltage is actually driving the charges inside the elements and causing the currents that produce radiation, and it's being emitted out. Right, that is how it works, except the acceleration is given by us right now. So you can see that as the charges move from basic electrodynamics, we know that along the direction of the acceleration vector, you won't see any radiation. And the maximum electric field strength of the transverse electric field strength, which causes wave propagation, is maximum in a plane that is perpendicular to this axis of the dipole. And if, for instance, theta is the angle that we are defining with respect to the axis, then the transverse electric field is proportional to sine theta, and the power pattern obtained by essentially squaring the electric field is sine square theta, and the distribution is how you see in the bottom figure. It's a polar plot where it essentially plots sine square theta. And if you see in 3 dimensions, it would form like a symmetric torus. And it essentially shows that along the uh, in the at the middle of the dipole along the horizontal axis, the power emission would be maximum, and it will go to zero at the along the axis, following a distribution that goes as sine square theta. Now, once we understand this, it's easier to relate it to a receiving antenna, where what's happening is we have electric fields that are falling on the antenna element, a dipole element, and you can see that when the electric field is parallel to the axis, it will cause the charges to move and have the maximum effect. Whereas when the electric field is perpendicular to the axis, it will have almost no effect to a contribution towards the current for a thin wire like dipole. And for a general angle theta, it will be proportional to sine theta. That is the, the electric field reduced by a factor of sine theta will be the one that will drive the current. So you can see the equivalence over here. Uh, the so the effective electric field will follow a sine theta dependence for the incident electric field, and hence the effective area, which we are defining as how well it can receive radiation along different directions, will follow now a sine square theta form, which is will be exactly like the power power pattern of a similar antenna if it were transmitting. It is a proportionality but not an equality, the effective area and the power pattern. So what we have is this effective area, which is actually designed according to the application we are interested in. We could have something this broad that is looking at all the directions, or most of the directions pretty broadly distributed. Or we can have ways to concentrate the effective area such that we are only focusing on some area of the sky, or a solid angle above the telescope, rather than looking all around. Now, once so this effective area is dependent on the shape of the feed element, as well as the uh, and once that is set, we could always change or redistribute this effective area by having reflecting surfaces like a horn or a reflecting dish and so on. So a dipole antenna which has a distribution of sine square theta for the effective area, proportional to sine square theta for the effective area, as shown in the picture above, it could be placed at with the appropriate reflecting surfaces or inside a horn, such that the effective area redistributes uh, such that it has a much narrower distribution, as you can see in the bottom figure, which is essentially if you design the horn of the antenna right enough, it will look something like this. So there is this, once the feed is designed, one can, I think the effective area is conserved, and you can use reflectors to redirect it such that you can get higher effective area than it was without the reflector. Now, just by these relations on the effective area should be somewhat obvious, that if you integrate the effective area of the over the entire 4 pi steradians, it could be expressed as average effective area times 4 pi, or we can also define maximum effective area, and let's say we divide that by the average times 4 pi, you'll get something called the beam solid angle. That's another quantity that you can that characterizes a telescope essentially, where it sort of gives an idea of how well the effective area is localized. Okay, so now we are back to our setup where we have an intensity distribution in the sky. The intensity couples to the antennas through the antenna's effective area, and hence it generates a power in the antenna, which is an integration over for a general case. It will be an integration over the effective area and the intensity distribution of the sky. Now, the factor of half in front is because looking only at one polarization with a single dipole. So this is the most general formula. What one can go ahead and do is define in the Rayleigh-Jeans limit. You can take the intensity of any particular source or any particular region of the sky, see how much flux it gives, and try to assign a brightness temperature to it. This is something you must have heard in the previous lectures too. But essentially, you're equating the intensity you're getting in a small band, and you're equating to, or you're finding out which temperature black body would produce a similar amount of flux as the intensity that you see. And hence, in the Rayleigh-Jeans limit, this would be the expression. It will be 2 kBT by lambda square. And what that allows you to do is convert that intensity distribution of the sky into a temperature distribution. And you can have an expression like this for the power that would be available at the antenna. Now, this allows us to, in principle, define an antenna temperature. That is something, again, you would have heard it in many of the talks, and you will be hearing. This module, actually, when you go through some of the sections, it will make more sense as to why we are defining antenna temperature at all. But for now, let's assume that we have a power received in a particular spectral range, and we can always convert it to a temperature by dividing it by the Boltzmann constant. And we can call that, instead of using power, we are just using equivalent term. Since it's a constant proportionality, we are referring to it as temperature, and that we are calling as antenna temperature. And from previous expression, you can see that you can hence get a relation between the antenna temperature and the brightness temperature of the source that you're looking at. This is the most general case. Of course, right now, it may not mean too much as to why we are doing this, but once you figure out using the worksheet, how one can calculate the total effective area, for instance, or in special cases where the beam is too narrow and pointing towards a broad source, or a source is completely covering the range of the effective area of a telescope, then we can simplify it, and we can get we can get a much more clearer relation between the antenna temperature and the brightness temperature of the source we are looking. So I won't say much more on this here, because I mean, it's better when you work it out. If you have this antenna and a radiometer, you can measure the power that is there in the antenna. You can always equivalently call it in terms of the antenna temperature. You will have access to the effective area of the telescope, either because of its reflectors and all that. It could be this well constrained or well localized, or it would be a broader distribution. But in principle, you'll have this value. And using this equation, in principle at least, you can model the intensity and try to get the intensity that is producing the power in your antenna. This is just I'm summarizing the general setup. What one can do is look at the special case of a black body and try to see how much power is generated from observing a black body. For this, there is a good little thought experiment one can do, where you start out with the lossless antenna, which is, it doesn't have any internal resistance, but of course it will always have radiation resistance, because if charges are going to accelerate, it is going to radiate, and that is a form of resistance. So other than that, it does not have any other resistance. And it's surrounded by a black body, and the entire effective area is looking at a black body of temperature, uniform temperature T. Now, in another cavity, there is a matched resistor. When I say matched resistor, the resistance is chosen such that the resistor's resistance matches the radiation resistance of the antenna that we have in the other path. And now they are both connected by a transmission line, which allows only electrical power transfer across it. So under equilibrium, uh, will have a condition where there will be no net transfer of power, so that the energy distribution will be the same, power distribution will be the same in a resistor of matched resistance and the antenna of a particular radiation resistance. Now I'll have to okay I'll leave it at this. Again, this is something um, you can use the setup and try to find out how the temperature of the path corresponds to the temperature of the antenna that we observe. Now that is again an activity, you will do it and you'll understand. But as long as you understand the setup, this will again be explained in the worksheets. And I just wanted to get you familiar with it. What we have in the setup is essentially a relation between the power distribution in an antenna and the power distribution in a resistor. And we have shown that it will be equal, at least in this particular setup. At this point, it would be good to know what is exactly the power distribution in a warm resistor. If it's maintained at a particular temperature, what would be its power distribution? For that, there's another experiment where you take identical resistors. The experiment is similar to the previous one where you have them in the same temperature. And here they're connected through by a transmission line of length much greater than the wavelength of interest to us. So we are measuring essentially the power distribution in a particular frequency band. Again, at equilibrium, there will be no net power transfer. And what we'll have in the transmission wave line is essentially standing waves. And standing waves are these are created when opposite moving waves of equal amplitude and equal frequency combine, and you can create these standing waves. It's just a tool that allows us to actually enumerate the number of energy distribution in different modes that exist inside a transmission line. That's why we are going about this particular experiment. So we focus on the transmission line. We know there's no power transfer, so the only energy distribution is in the standing waves in the transmission line. And we have chosen the length so that we are in a regime where there's no the quantization effect is not too much. We essentially have a continuum of states. Yet still, because we have a particular length of the transmission line, we are able to still count the states at lower wavelengths, apply the same formula for throughout its um, throughout its frequency range, and essentially get the power distribution in a frequency band. So it essentially, as you'll see in the experiment, it will essentially help us count these energy states. So what we'll do is we'll count the number of modes that exist in a frequency band. It will be more obvious at when we start counting from the largest wavelength it allows and count up. For instance, the modes that are allowed are shown by the schematic at the top of this circuit. There the nodes will have to go to zero at the ends of the transmission line for it to be a standing wave there. And one can essentially count the number of modes exist in a particular frequency range. Once you have that, you can calculate the average energy per mode using the Boltzmann law, and you can calculate the time it takes for you know this energy to transfer through the transmission line, and essentially you get the power right out of it by multiplying the number of modes per frequency band by the average energy to get the average energy per frequency band, and you convert that to power by trying to see how long it takes for it to traverse a particular distance. So in summary, what you would have learned, what will become clearer at the end of working with this worksheet is that you'll see how electromagnetic spectral intensity is converted to electrical power in a frequency band. And we'll see how a natural way of talking about electrical power in a radiometer is to use refer to something called the antenna temperature. And then we'll also see the equivalence between antenna noise and the noise of a warm resistor. Together, it will sort of form a consistent set of ideas that give an idea of how what kind of electrical power is generated in the radiometer uh, due to the radiation that is being sensed by the antenna. So you'll notice that the order of these sections are sort of reversed in the worksheets themselves. I mean, Desh was the one who convinced me that this is the right order to go, which I agree. I do think this is the right order. Um, Between, because there is a small problem that in the worksheet it might give you the false impression that the black body is somewhat special, and some of the relations you're finding out applies only if you're looking at a black body, but it's more general than that. So between this presentation and that worksheet, I hope you get a more consistent picture. You should always refer back to these presentation when you're working on this the worksheet.
There are two things that I couldn't understand. One is what is the significance of having L much greater than lambda? I mean, I couldn't uh, understand that one thing. And second thing, will this not be only able to measure low energy modes the way if we arrange it with L much greater than lambda? I mean, how are we actually then going to measure uh, higher energy modes? I mean, so it's basically related to the fact I'm not able to understand L much greater than lambda here.
I would say it's the other way around. We are setting it so that we are able to achieve pretty much continuum distribution across all modes, or all frequencies are allowed. So what it does is this when we are counting these modes at very low lambdas, um, no, not very low lambda, these high lambdas or low energies, what we are doing is establishing a way to count these numbers. We are essentially using this to determine what is the functional form of number of modes per frequency band. But we are not actually we are not interested in this distribution at such low energies. Eventually, we are interested in the distribution of number of modes per unit frequency at higher energies. It's just that this gives an easy way to count them, and then use only the uh, expression in the higher energy limits. Does that make it clear? Because here what happens is the quantization makes it so that most of the energy just goes into these very specific bands. But in a resistor, it would be at all frequencies essentially. Does that make sense? Like in a resistor, it won't be quantized like this. We're using this quantization in this transmission line so that we are able to count it. We can determine the functional form of delta n by delta nu, apply it in the regime where the effect of quantization is negligibly small. Essentially, there are a lot more modes per frequency band. It's a simple tool for that. Desh, maybe you can make things.
Yeah, I just want to continue on what you said. Just say it again, that for convenience of computation, one wants things to be quantized so that one can count. But in doing that, the graininess is to be reduced to very fine level so that there is a effective continuum. Okay, and that is done by setting L much larger than whatever frequency of interest, so that the graininess in frequency is very tiny. So you practically have a continuum, but you have the advantage of estimation using the discreteness.
Yeah, I got it. Thank you.
So L going to infinity is what one is looking at, okay, where it's mashed to R, okay. So there are in equilibrium there are no reflections. Everything is absorbed.